working as a software engineer and leading the virtual machine team. So the idea behind this talk is to zero in on the effect of EOF, the Ethereum Object Format, on developer experience, developer tooling, and to focus primarily on debugging. Hopefully by the end of this talk I will convince you that EOF will make it possible for the Web3 debugging experience to be miles ahead in comparison to Web2. Currently, there are many debugging issues in regards to Solidity. Everyone who's ever written a smart contract knows how hard it is to debug it during development and after it goes into production. Broadly speaking, the issues could be bucketed into two groups. One of them is the fact that we are lacking a proper debugging format, and the other one is the fact that you could execute optimized and non-optimized versions of the same contract and get different results. These two issues are, in a sense, intertwined. So let's say that you'd like to debug a program in traditional programming / Web2. You would need to debug it using the debug release. If you would use the release executable, you would have much less debugging info, therefore you would have much less data about the state of the program at the point that you were trying to debug. So the issues are that in order to have the exact same amount of data when you're debugging Solidity, you also need to debug it using the debug release / executable, which means that you would need to debug the unoptimized bytecode. Since there are differences in execution between the optimized and unoptimized bytecode, effectively you could have a debugging session that's been running locally, where you've executed a certain code path, and when you replay that input in production or in a local session using the optimized version of the bytecode, you could get entirely different results. The main culprit behind this is the gas opcode, which is being executed every time there is a call, and which can also be injected into the execution via an assembly block. Let's say that we've got both the optimized and unoptimized versions. Their gas consumption is different. Therefore, the value that will be pushed in at the stack when a gas opcode executes will also be different. And if a control flow consumes that value, we will get different results. Therefore, we cannot be sure that when we are debugging using an unoptimized version, we are actually looking at the things that we'd like to see. And the lack of a proper debugging format disallows us from having the exact same data granularity that we would have while debugging in a traditional programming language. EOF offers solutions to these two problems. By changing the structure of the EVM, it will be much easier to define a proper debugging format and to extract the same kind of data that you are able to extract in traditional programming languages. But there is also one extremely interesting development that happens inside of the EOF that allows us to have semantically identical executions between optimized and unoptimized versions of the bytecode. Gas opcode is removed, as well as other opcodes whose output depends on the code structure, such as code hash, code copy, external code cache, external code copy. Therefore, when we get to a debugging format that will allow us to extract the same kind of data, we will be able to spin up a debugging session that will have the exact same output with an optimized bytecode and an unoptimized bytecode. And this is my final step towards convincing you that Web3 debugging experience could indeed be better, but I'm running out of time, so I will be quick. Let's take a look at a single request / transaction. Let's make it an HTTP standard request that lands on a server. So every program that executes has two kinds of input, a code and state. When you land on a specific server, the state that you're getting as input is fragmented. It's either in Redis, it's either a local variable, it's either in Postgres. But if you execute a transaction on the blockchain, the state is localized. Therefore, you can replay the exact same input that you had in production, if a transaction, let's say, failed, in your local development environment. And if you're able to extract the same kind of data via a new debugging format and have the same execution in unoptimized bytecode as in optimized, you basically can replay every production request locally with the exact same environment as in production. And that's it. Thanks.
Thank you very much for the presentation. So we don't have any questions yet. I have one. Is there any implementation of a debugger that uses EOF so far, or not yet?
Not as far as I know. This is a thesis. It can be looked at it that way. Mm-hmm. Some of the clients have implemented EOF, but some have not done it yet.
Okay, let's go to that question. Do you have any insights on if EOF affect source code verification?
I'm trying to think off the top of my head. I do not have any insights as of right now, as I haven't thought about it. So source code verification. Okay, so yes, it does affect it. Source code will be verified on the protocol level every time a contract is deployed. There will be no need for jump test analysis every time jump desktop code is executed, as it is removed from the virtual machine altogether in EOF contracts.
Mm-hmm. Let's try to answer one more question. Which difference besides gas consumption can be between optimized and non-optimized code?
So optimized code, depending on the number of iterations that you optimize it with. So there's a flag that basically says, I want this contract to be executed optimally if it is executed X times, and you can say that it's 1,000 times. So if it's executed 1,000 times, on average, it should have much less gas consumption than in comparison to the non-optimized bytecode. So optimized bytecode can throw out entire sequences of the bytecode. It can also merge sequences of bytecode. And every time you change the bytecode, you basically affect the gas consumption